Friends, welcome to the first live session of the Irrigation and Drainage course. So I'm here, everybody knows my name, I'm Dr. Mailapalli. I'm an assistant professor here in Agriculture and Food Engineering Department, IIT Kharagpur. First of all, I welcome you all for this course, and I'm happy that there are about 1100 students or opted for this course, okay, and then around 17 students were registered for writing the exam, and I hope you are enjoying the course. We are also seeing your responses for the assignments. So if you have any question for the past, I think 8 weeks or 7 or 8 weeks, so let's discuss here, please. So this is basically a 12 weeks course. We have basically divided the whole into 6 module, and so the 6 weeks and 6 weeks. So 6 weeks on irrigation and 6 weeks on drainage. So focusing on different fundamental aspects of irrigation as well as drainage. So we initiated first, the week 1 with the basic definitions, the introduction, and then in the second week we focused on the different soils and the soil water, and followed by water balance, and then water application methods like irrigation, surface irrigation, subsurface irrigation, and sprinkler irrigation. So and then we focused a little on groundwater, like well hydraulics and then the pumps, and then followed by drainage issues like different drainage types and construction of drainage, principles of drainage, and also some software things. Okay, so softwares in both irrigation and drainage. So this is a whole course. Total, as I said, is 12 weeks. Basically, I'm happy that we are running this or rerunning the course in this year, and also the next year, and also 2021. So we have a question here. So which state government in India has properly planned irrigation and drainage? Well, this is a general question we received from whom? What is his name? Huh? Jai Krishna Reddy. So, so the state governments here, most of the state governments are aggressively working on irrigation, right? And the drainage is not the many states' problem. There are specific states. For example, the what you call the other side, the Punjab is one of the states. Okay, so irrigation is concerned, properly planned irrigations. There are many. So, for example, Andhra Pradesh and then Maharashtra. So, these states are aggressively working on irrigation, like micro irrigation. They are introducing new technologies in their farming, like Telangana state. So, mostly the southern states are more aggressive, and also the drainage, like the Telangana state as well as the Andhra Pradesh state. Okay, so and then there is another question we received from Srikanth Madugala. So his question is, what is the basic difference between permeability and hydraulic conductivity. Okay, so this question really, I mean, sometimes it confuses the people what is permeability and what is hydraulic conductivity. So, though it refers to the same the concept, but the thing is, if you see, the permeability basically refers to the property of a media, the soil media. Here our context is soil, whereas hydraulic conductivity, so that refers to both soil property as well as the water property. It contains both soil and water property. So, you have some equations that will basically tells whether this particular property refers to a soil property or media property, or is both. For example, the permeability, if you see the equation, I think I can open the what is that? Okay, so this one, for example, I am going to strike it off. How do you do that? So, anyway, so that is another thing. Yeah. So, here if you see the permeability, so which is basically denoted with small k, right. So, small k, which is equivalent to C d square. So, where so d here is the diameter, like average diameter of the soil particles. So, this basically refers to soil property, okay, and k is denoted with Darcy's. So, 1 Darcy is equal to 9.81 into 10 power minus 13 meter square. So, this is 1 Darcy, right. So, whereas k we denote with capital K, this is capital K, which is derived from Darcy's equation. So, that is Q by I into A. Okay, so, that Q is equal to K I A, or K is equal to Q by I into A. So, in this case, the K here also written as the capital K, which is equal to small k into rho divided by mu, where rho is the water density and k is the small k, which is permeability, and mu is your dynamic viscosity. So, if you see this is the property of media and this is property of water. So, it contains both fluid as well as water property. So, K here what we are talking here is the saturated hydraulic conductivity in this equation. Generally, the K we derived from Darcy's is the saturated hydraulic conductivity. If you define the K value, right. So, define K values, this is from the equation straight away you can define. So, for unit flux of water per unit hydraulic gradient, the flow through soil media, saturated soil media, will be equal to saturated hydraulic conductivity. So, generally we use saturated hydraulic conductivity for estimating saturated hydraulic conductivity. We will be using Darcy's equation. For unsaturated hydraulic conductivity, we will be using the Richard's equation. Okay. And do we have any other questions? Okay, so there is another question. This is, I saw a term AWD in week 2 lecture 2. So, what is AWD and what is the difference between AWD and conventional? So, I know. So, I think so basically the AWD and conventional, what we are talking here is the irrigation methods generally we practice for a rice crop. Okay. In conventional case, what we do is during the base period, so we will be maintaining certain ponding depth. So, the ponding depth could vary from 5 to 10 centimeter. So, so the irrigation could be practiced in such a way that when the ponding depth basically depletes to 2 or 1 to 2 centimeter, and you are going to supply the irrigation and make it up to the say ponding level like 5 or 10 centimeters. So, that is a conventional way. So, that means the advantage of this is you are restricting the growth of the weeds. So, that is the advantage, so that the food or the nutrients which are consumed by the weed could be saved for the crop basically. Whereas AWD, so this is alternate wetting and drying method we called. So, in this the name itself indicates like irrigating the the rice crop alternatively. So, alternate wetting and then the drying. So, it is like we have here wetting spots and drying spots. I mean generally this is different from what conventional irrigation method, where we see only the wetting spot throughout the base period. So, the advantage of this method, the alternate wetting and drying compared to conventional, is that we could save 30% of water. Generally, in conventional or traditional way of irrigating crop can consume around 100 to 150 centimeter the whole season, but you can save 30% of that. So, that means you can grow another crop in parallel to that during that time. Okay. So, that is advantage. Generally, the alternate wetting and drying could be practiced in the farmer's field in two ways. One, you can install a perforated pipe, we call it as pani pipe. So, monitoring water level in the perforated pipe in such a way that so we initially keep the ponding up to 5 to 10 centimeter, and then let it deplete till 15 centimeter down the soil. Then we are going to irrigate. So, we are going to irrigate the crop and make the ponding level up to 10 centimeter or 5 centimeter. So, that way the irrigation practice will continue during the base period. Okay. There is another method that is called using the different levels of moisture stress. Okay. So, using the tensiometers. So, tensiometers, so you can generally for saturation this will be 0 millibar. Then you are going to let the soil keep under soil's moisture stress. So, that could be like go to 400 millibar or 700 millibar. So, different soil moisture stress levels. So, that is the target level, your target level. So, based on that, once you get the soil moisture up to 400 millibar or 700 millibar, you are going to irrigate the crop. So, this way also you can save a lot of water compared to conventional method. So, this is a little now the AWD practice has been promoted to different farmers fields. Even the World Bank also looking eagerly. Recently, we got a project from the World Bank in our department. So, that is automatic irrigation practice used for the rice crop by getting a cell phone message from the field to the farmer's cell phone, and then based on that the farmer will decide when to give an irrigation based on the alternate wetting and drying practice. Okay, so I hope we have another. Okay. So, we have another question from Bindu. Hello sir, what is a geological formation and what are different types of aquifers? Okay, so this is regarding, I think, the groundwater, okay, so well hydraulics. So, the geological formations are generally found when you dig a hole from the surface to ground. Okay, so this is basically, if you see these, I mean the stratum, we call it the soil stratum. So, if you take a dig from the surface to bottom, you will see different layers of soil. Okay. So, the particular layer we called a geological formation. So, generally the geological formations could be like aquifer, right. So, we call this is aquifer because so the mostly the geological formation which holds water and at the same time it transmits water. So, it is like it takes water and gives the water back. So, that kind of property if the geological formation has, we call that aquifer. So, for example, sands could be a good aquifers, okay. Sands could be a good aquifer because it has definite pores and the water can be intact or inside the pores of sand particles as well as due to gravity. So, the water can be transmitted back. Okay. So, that is the best example for aquifer. So, the next geological formation is aquifuse, we call. So, the aquifuse in the sense it does not contain any interstitious pores, that means a solid rock. Best example is the granite. So, the definition is like it cannot hold water and it cannot transmit water. So, that is aquifuse. And then the third is aquiclude. So, okay. So, aquiclude, the name indicates the clude, to me it resembles like a clay, okay, it is a clude. So, aquiclude, that means it holds water, but it does not transmit water. Okay. So, the clays are good example. So, clays will take or absorb water, but it is very difficult to transmit water. Okay. So, this is called aquiclude, and the fourth class is that is called aquitard. So, the name indicates like aquitard, retard. Retard means the aquitards are probably the good aquifers long ago, but over a period of time the clay or silt particles intrusion into the interstitious pores between the sand particles. So, that basically clogs the pores and then it loses the property of aquifer. So, that means the good aquifer over a period of time loses its property and it is a retards, basically that is called aquitard, and best example could be sandy silts. Okay. So, that means the sand and then silt particles which are sitting in between the pores. And the main but it has a major role, it has some influence on the neighboring aquifers, because aquitard means it is not completely retard, it has some low hydraulic conductivity. So, that definitely influence the neighbor aquifers. So, these are the four classes of aquifers, geological formations. And then the other question is what are the different types of aquifers. So, the aquifers basically it could be unconfined aquifer based on the type of geological formation you are observing. So, one is unconfined aquifer, the other one is confined aquifer, leaky aquifer, and then perched aquifer. So, there are four kinds of these aquifers. So, in case of unconfined aquifer, so the impermeable layer will be at the bottommost and then the aquifer will be sitting on top. So, that way, so for example, here if you see, go back, pen, highlights, okay, so next page, okay, good. So, if you see here, in this case, so this is the surface, right, and this is the bottom we called bedrock. This is the bedrock. Okay, this is the bedrock, and if you see the geological formation, which is an aquifer, so that means the aquifer is sitting on bedrock. This is unconfined. This is called unconfined aquifer. This is unconfined aquifer. Okay. So, here the imaginary surface you see, that will be the water table. This is called a water table. And how do you get this imaginary surface? So, that is by installing different observation wells. If you have different series of observation wells installed, and the levels in the observation wells indicates the water table. Okay, so then there is another kind is called confined aquifer. So, that means if this is the surface and if this is the bottom, this bedrock, and this is another layer, this is also impermeable layer. So, there is an aquifer which is underlain and overlain by two impervious layers. So, this is called confined aquifer, and the pressure or the imaginary surface which you found or observed will be called piezometric surface. So, the similar to in case of unconfined aquifer, if you install a series of observation wells, the water level if you see in the observation wells will give you the piezometric surface in case of confined aquifer. Okay, so, this generally the piezometric surface will be more than the atmospheric pressure, whereas in unconfined aquifer, so this the top you see the the atmospheric pressure. So, the wells which are connecting to this unconfined aquifer, we call this phreatic wells. This is called phreatic wells, or you can also call what you call water table wells. So, in case of confined aquifer, these wells, the main wells we are talking, these are observation wells I am showing here, but if the wells are connected to confined aquifer, we call them as artesian wells. So, if the level of the well is below the piezometric surface, and so the water will be flowing continuously, then we call that is a flowing well. So, there is a third case we call, so this is the bedrock, that is the leaky aquifer. So, the aquifer is overlain and underlain by a semi-impervious layer, which is called semi-impervious layer, or this could be a this could be impervious layer. Okay. So, that means if the aquifer is underlain by impervious layer and overlain by semi-pervious layer, so we call it as leaky aquifer. Okay, this is a leaky aquifer. So, that means there is a recharge could be taking place from top to bottom to the confined aquifer. Let us say it is a similar to the confined aquifer. And the fourth one is perched aquifer. So, that is just within the unconfined aquifer. If you see, this is a special case of perched unconfined aquifer. You see the water table, this is called perched, this is called a perched aquifer. Okay, perched aquifer. So, this is basically happens when in the local conditions. Suppose there is a silt deposition which is taking place here, or the clay deposition, and there is a particular layer. So, the water will be stagnant here, right. So, this you can tap this water through a perched well. Okay. So, this is a locally identified you can say the unconfined aquifer. Okay. So, these four types we could see as the different kinds of aquifers and also the corresponding wells. Okay. Any other question? All right. So I will continue with few questions, forum questions during the assignments time. So I got this is from one question from Pankaj. So he saw like productivity is 2.5 ton per hectare for irrigated area. So his question was like, how is it possible? I am doing farming with my fathers for an years. In Rabi, we are having about 23 quintal per acre, that's a wheat, and about 30 quintal per acre in Kharif. So he was just wondering how it could be like 2.5 ton per hectare for irrigated area. So if we have like this, the unit conversion, if you convert it, so the wheat could be like 5.68 ton per acre, but based on his calculations, and then the rice could be like the maize could be like 7.4 tons per acre, but in the the PowerPoint what we are talking about is 2.5 ton per acre. I mean, this is very good question because this is for a particular farm, and it also tells us how the production is variable from farm to farm. So he might be getting good yield, but the number what we are showing here is that average yield for the country. Okay, so that way you can see there are some cases which have less than 2.5 ton per acre. Okay, and we have another question. So I will continue with the forum questions, but this is another question. Sir, can you explain what is drawdown curve? Okay, so drawdown curve, what we are talking here is referring to tube wells. So as I mentioned, I mentioned the different kinds of aquifers, right? So initially, so the aquifer will have the water which is saturated condition. Okay, so that's called the level, the top of the saturated the stratum we call the water table in case of unconfined aquifer, and in case of confined aquifer we call it as piezometric surface. Okay, so that is also called, it's a static water level. Okay, so that's a static water level before pumping. So when you start pumping from the well, what happens? The water level in the well is going to deplete because you are taking the water out. That's only visible part, right? From the well point of view, you can only see there is a depletion in water level, but inside the soil, so that's not taking place like linearly, it is going down. Okay, so the points which are nearer to the well are going to deplete faster, and if you go further from the main well, the depletion rate will be slowed down. Okay, so here in the main well, from the difference between the static water level and the pumping water level, we call it as the drawdown. Okay, so similarly, if you go out from the well and within the soil, if you see the difference again, so there how do you see the difference? Because there is no visibility like in case of well. So in order to see clearly, you have to install observation well. So observation well is mainly to record the reading, it's not for tapping the water. Okay, so assume that you have series of wells from the main well at certain distances. Okay, from the main well to, so different observation wells are installed. So if you can take readings from the once you finish the pumping water level, like pumping is done, then collect the data from individual wells. Then you would see a curve like this. If you suppose this is the surface, okay, and this is the bottom, what we are talking, this is the bedrock, okay, this is the bedrock, and as I said, the initial this is called the surface, right. This surface we call is a static water level, right, static water level before pumping. And suppose you have a main well here, and the water level here will be the static water level. The moment you pump this water, so this is going to be at this level because of the pumping. So we know here this is the loss of water, but we don't know what that effect will be farther from the well. What is going to happen here at this point? Suppose if you have a well here, so what is the influence of this pumping on this, and what is the influence of the pumping at here, at here, at here, at here, okay? So in order to know that, let's install observation well here, 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 1, 2, 3, 4, these are observation wells, and now find out the water levels. For example, if you see the water level will be almost not at this level, but definitely a little higher side, and similarly here, similarly here, okay. So then if you can join all these differences like static, so what is this difference and this difference and this difference, this is called drawdown, and if you can combine all the points, okay, so this is basically called a drawdown curve, because it represents the drawdown in the soil stratum from the main well, okay, from the main well to a distance. So this is a drawdown curve. So since we assume that this is soil is homogeneous, so we may get a regular curve, a nice curve like this. So similarly, the other side you get, okay. So since we assume that this is the radial flow, okay. So water is flowing horizontally and radially. So that means on top, if you see, so water will be flowing like this from all sides, okay. So this way, all right. And this is very important, and this will vary from soil to soil, and like a different confined aquifer to aquifer, okay. Okay, so this we got another question. This is Jishita Prajesh, okay, sorry. Sir, how can efficiency of border and furrow irrigation be found practically from field? Is there relation between advance resistance and efficiency? Is there relation between, what is that, advances? Advance resistance and efficiencies. So the question here, so the question is how to find out the efficiency, the irrigation efficiency of a border and furrow irrigation practically from the field, basically. So you have the equations, you have theoretical background, but the question is how to find practically in the field furrow irrigation. Suppose you are starting delivering water in a furrow irrigation, okay. So how to find out the irrigation efficiency of that? So that what I would do, basically in order to find out the irrigation efficiency, we need to know the waterfront advance and also the infiltration profile. So infiltration profile is very important here, okay. So infiltration profile is very important because the whole efficiency term is linked to your infiltration. So how to find out the irrigation I mean this infiltration profile practically in the field. Okay, so that is the question for furrow irrigation versus the border irrigation. So, I mean the both cases, so the basic our question is to find out what is the wetting front advance, basically wetting front advance, that means downward movement. Okay, so once we know the downward movement at different locations, so what we have to do is we are going to get that information and plot it and find out the average. Okay, so I mean average what you call this area, and you can estimate using the equation I proposed in the slides. So the question is how to find out that wetting front profiles. Okay, so the best example is, I mean best way is, so you should find out what is infiltration the curve for the particular location. Suppose you have 100-meter field, okay, 100-meter irrigation field, I mean practical field. So at least let's put in the first head end you have infiltrometer, okay, and then the different locations, so you have infiltrometers. So because infiltrometer will tell you the point measurement. Okay, so similarly you suppose in the first let's say every 10 meter you have infiltrometers. So because the soil is not uniform, so you will experience the soil, the variability or the infiltration characteristics are going to vary over a space. So the infiltration characteristics of one point and second point, third point, like that . So knowing the infiltration characteristics, okay, and then how long you have been irrigating, right, and knowing that information and knowing the advance times, so you will be able to find out the infiltration, that vertical infiltration at that point. Okay, this is one way. So I also explained in the notes, if you have like advance curve, you can estimate infiltration characteristics of the field, and using the infiltration characteristics you can estimate the infiltration profile. So knowing the infiltration profile, so the what is the amount of water which is infiltrated down. So that is that's what we expect the output. The input is the water you supplied, that Q naught into T, that's what you supplied it, and then the the infiltration, the what you call the infiltrated area. So that will give you the efficiency term. Okay, and there are, I also explained different ways in case of furrow irrigation, like last we'll consider the last quarter, the area. Okay, so that's very important. So knowing the advance curve, you will be knowing the infiltration characteristics, and from there you will profile the infiltration and then estimate the efficiencies. Okay. Similarly, the border irrigation also, you have advanced curve, or you have already done the infiltration experiments using ring infiltrometer. So knowing the infiltration characteristics of the soil, you will be able to find out, you will be able to profile it and then find out the efficiencies. Okay. And is there relation between advance precision and efficiency? Okay, this is a good question. I mean, is there any relationship between advanced precision and efficiencies? Okay, so the advanced and precision, if you see that the difference between precision and advanced, so that will give the opportunity time. Okay. So the opportunity time is linked to your infiltration. So that's the infiltration. So if you take the opportunity times at different distances, so that will give you the whole I mean, if you plug that opportunity time into infiltration equation, you get the infiltration, that infiltration. And you only need that once you know the infiltration, then finally you know how much water you supply, and the infiltration, the total infiltrated area divided by you get the Q naught T, you get efficiency. There is a relationship anyway. Okay. And no question. Okay. So I mean, for both border and furrow, the main difference is the width. Okay. So in the modeling, what we do is we use the furrow irrigation model for modeling border irrigation by considering its width. It's a broad width. Okay. There you have the 30 centimeter width, but in case of borders it can go up to 1 meter, up to 1 meter. So in the equations, the Saint Variant equations, when you solve these equations, so the width term, what we are going here is considered, okay, I mean broader furrows. We consider border as a wide furrow. Okay, so that way you can also solve the border irrigation, advanced, resistant, and all irrigation problem into a furrow irrigation. You can convert that into furrow irrigation. All right, so we have this is one forum question. The other forum question, this is from Arun Kumar. So his question was, in general, pond area is considered under GCA, that is a gross combined area, and exclude in culturable combined area. That suppose if you have a pond, we will consider that in gross combined area, but not in culturable combined area. However, in pond area, because in the slide we mentioned that ponds can be excluded from culturable combined area. However, in pond area we plant crops like foxnut, rose flower, etc. So will it come under culturable combined area? If yes, how we can calculate its duty? Okay. So remember, the duty and delta, what we focus is referring to the canal level. It's not like farm level. So the moment we are considering the ponds, right? These are local ponds. So suppose if the ponds are getting water filled up by precipitation, right? So those ponds, because the CCA, culturable combined area, we are accounting at canal, through canal water supply basically. So since it is locally managed, so this may not be coming under the culturable combined area, even if you grow crops with the ponds. But you can also consider, if you are still diverting water, the canal water, filling up your ponds, then yes, so that could be under culturable combined area. So this is the question. And there is another question from Sandeep. He was just asking what is a crop year. So the crop year generally, the harvesting of a crop to the next harvesting of the crop. Okay, this is the time period between the two harvesting periods. Okay, this is the crop. This is what we got from the forum. So this is up to, I think, 8 weeks. Now right now 8th week is running, and we also uploaded the assignments for other weeks. So if you have questions in the forum, you can post it. And this is the first live session, but we are going to have 2 more live sessions. So that will be scheduled. It's already scheduled, but we are going to update on that very soon. So still we are looking for questions. So no questions. Okay. Right. Okay, so the no question, then so if you see, we call Darcy and Ohm, right? So they are called like brothers of science, we call. So why we call them brothers of science? Because Darcy's law and Ohm's law, they look similar. Okay, so because they both talk about current. Current in the sense here the real electrical current, and there water current. Water current is water basically. So basically this flow in porous media, like in saturated media, so that is defined by Darcy's law, whereas electrical current which is defined by Ohm's law. Okay, if you see both equations, Q is equal to KIA in case of Darcy's law, and in case of Ohm's law, I is equal to V by R. Okay, so that's a V by R. So in both cases, if you see here, I is the current and Q is the discharge. Okay, that's a discharge. Both refers to the same, flow. And Q is equal to KIA. If you see, Q is equal to, right, K, I and A, versus V, sorry, what is that? All right. Okay, so let's say, so this is I is equal to V by R. Okay, so this is the flow rate and this is current. Okay, so here the gradient what you are showing, this is the gradient, so that is equal to your the V, that's a voltage difference, and then so R here, this is a resistance. Okay, so resistance, so what we do, the resistance here will be, so here this is delta H by I is equal to delta H by delta L. Okay, that's delta H by delta L. So delta H basically refers to your voltage, and here K, if you can bring it down here, that is delta L by K. So this basically refers to your resistance. This hydraulic conductivity, inverse of hydraulic conductivity is the resistance. So this way, the both laws like Darcy and Ohm refers to, they are parallel laws, or I can say. So one refers to discharge, the water, the other one refers to current. Any other questions? Okay, 10 more minutes. Set. Okay, so I would like to add few more informations to the previous question, that's on the AWD, alternate wetting and drying, and the conventional irrigation. So the basically if you see the evapotranspiration, so I mean that's a very important parameter to estimate the crop water requirement. So FAO has developed given a tabulated values for rice crop for different growth stages. So we got the Kc values. So using the Kc values, you can estimate ETC is equal, that is crop evapotranspiration is equal to ET0 multiplied by Kc. Okay. So this is the basic formula we use for estimating ETC using Kc value and reference evapotranspiration. So for a rice crop under conventional irrigation practice, the Kc values are available and those are like generalized, and for local you have to again adjust those Kc values. But in case of alternate wetting and drying, so since the irrigation method consists of wetting spots and drying spots, the evapotranspiration, estimated evapotranspiration may not be same when compared to the conventional case. In conventional case, you have a long wet spot, so in the base period. Okay, so that means the soil is or the crop is getting enough water, the always saturated water, and it is not under water stress condition. But whereas in case of alternate wetting and drying, in some instance you are going to have dry spots. So that means the soil may have the soil moisture which may be less than the field capacity sometimes. So in that case, we may have to revisit the equation and we may have to multiply with another coefficient. So that's called Ks, that is soil water stress coefficient in case of alternate wetting and drying. So the challenge is how to find out the Ks. Okay. So finding the Ks is really a big challenge here in case of. So FAO has suggested a few steps to find out the Ks in case of water stress conditions. Okay, ETC is equal to you have ET0 into Kc into Ks. So that is the formula generally we. So the Ks is suppose if you have saturated condition, you will have Ks1 and Ks not equal to 1 in case of unsaturated condition. So generally this is let us say RAW, which is greater than theta. So your theta is greater than RAW versus theta is less than RAW. Okay, so your theta is suppose not this one. So your theta is greater than RAW versus your theta is less than RAW. In case of RAW, theta greater than RAW, Ks is 1. In other case, we have Ks less than not equal to 1. In this case, we have some formulas to find out Ks. So that Ks, which is equal to TAW minus D divided by TAW minus RAW. Okay, this is the formula this FAO has suggested to use to find out Ks value. So TAW is the total available water, and RAW is readily available water. And so TAW has a formula, so that is called theta FC minus theta wilting point. Okay. And RAW is equal to some P times TAW. Okay, this is a fraction of TAW. So mostly the P value varies from 0 to 1. In case of rice, we take 0.4 as P value. Okay, and the D is here theta FC minus theta I. Okay, so I is the initial moisture content. So based on this equation, we will be able to find out the Ks value here. So in case of alternative by dry method, so you have to the Ks is going to decide the ETC value basically. Otherwise, it's the same as the conventional method. Okay, and recently we published the paper on this. Maybe you can. Oh, it's no, internet is not available here anyway. So that is you can look into that. Shaker. Sorry, it's not yet good. Oh, first of all, I need to close this. First clear. Okay. So it's like Shaker et al. You can see 2019, and this is published in Paddy and Water Environment. Okay, so recently published. So you can go through this paper for estimating ETC under AWD, alternate wetting and drying method. Okay. So 2 minutes. So again, the drawdown curve. What again? Let's say the new one. So the drawdown curve we were talking about before. I think one of the viewer has asked. So what is a drawdown curve? Explained, but at the same time we can also see this drawdown curve experimentally in the field. In the laboratory. So suppose if you have a box like this. Right, like a sandbox. Okay, so the sandbox if you have, and so let's say so this is filled with sand, and you have in the bottom, let's say you have different holes made, and all the holes are connected through a manometer. Like let's say you have series of manometers here. Okay, so these are connected to individual manometer. All right. So if you saturate first the soil, just saturate it. Suppose this is filled with the soil. Let's assume that this is saturated completely, right? and let us assume there is at the bottom you have a drainage point. Okay. So, you have a drainage point, let us say that is going down, you have a drainage point here, and initially it is saturated, and if you observe the manometers readings, so all will show the same level, because that is the water level which is inside the sandbox. So, the moment if you open this, so that means draining is taking place. So, that is assume that that is as like as pumping, okay, like as pumping. So, then if you observe that slowly the water level in a manometer which is close to the drain pipe is going to recede or deplete faster compared to the one little away. Okay. Then if you combine all the points here, water level in the manometer, right. So, that will clearly give you the drawdown curve basically. So, that will give you the drawdown curve. So, this was observed in our experimental the lab experiments, and explained to the students, and so they could understand very nicely. So I mean, you can also try this if you have laboratory set up in your or it is very simple to make in order to see this. So, it is just a sandbox, and then connect the make holes at different distances, equal distances, and the connect to the manometers, and or you can also try putting another what is it clear, okay, this one, okay. So, you can also put another well here, I mean drain point, another drain point, and now you could see the influence of like two wells, like this is one well point and this is second well point, and you can study the well interference. Okay, you can clearly see this is called drawdown curve for well 1, and this is drawdown curve for well 2. So, you can clearly see where exactly the two drawdown curves are interacting or intersecting. Okay. And also you can study several things with the sandbox experiments, right. You can study multiple wells, you can also study the wells in series, you can study wells in different random positions, and you can evaluate the corresponding equations. So, I did not I think I did not mention the well interference in this, but definitely in your like the class exercises you can study several things here. Any other question? So, actually we announced this live session few days back. We were expecting questions from the participants. So, we did not get many questions. So, hopefully the next live session. So, we were expecting from the participants at least some questions, so that we can practically spend some time So it's like okay, so that's what expectation next session. And for anyway, forum is, I mean, the discussion forum is open. So if you are not attending this session, you can attend the following sessions. So if you, even if you are not finding time, so still we have options open through discussion forums. So get in touch with us. So we have 2 TAs, PhD students. So we'll be working on your, the queries, and hopefully we'll respond to the queries within time frame.